Excellent. All right. Well, thank you, everyone, for attending this first interactive session for the workshop Beyond mAP, Reassessing the Evaluation of Object Detectors, or its nice abbreviated form, BMREOD, because I'm uninventive when it comes to abbreviations. I'll just start off with a quick presentation outlining what this workshop was about, and then we will introduce our panelists and get started with some fun back and forth Q&A questions. So I hope you enjoy it. All right, first I want to give a big shout out to the workshop organizers for helping make all this happen. So it was myself, there was Niko, Flas, Gustavo, and Chunhua. So a big thank you to all of them for helping to get this workshop off the ground. All of them can attest to the fact that behind the scenes on the very first day it was proposed, it was a bit of a rush making it and putting it together. So a big thank you to all of them. So if I was to summarize this workshop in a sentence, it is one of the sentences that we have on our workshop page, which is that quantitative results should be easily reconciled with the detector's performance in applied tasks. Basically meaning that for any sort of evaluation measures or any sort of way that we are evaluating our object detectors, we should be able to easily translate what we see in our numbers to what we see in front of our faces, exactly how the system is actually performing when used for a given task. The general goals of this workshop were to try and identify any gaps that may exist in our standard evaluation procedures for object detection, to try and promote any alternative approaches to evaluation that addresses any of these gaps that enable us to gain increased insight into how our detectors are actually working, and to better equip us to start applying object detection to real-world problems with some degree of confidence. It was also a platform for us to host the third Probabilistic Object Detection Challenge, which was a challenge designed to promote object detection with meaningful spatial and semantic uncertainty output for robotic applications. For this workshop, we have a total of 12 presentations. We had 3 invited speaker talks, 2 self-indulgence organizer talks, 4 workshop papers, and 3 papers from the Probabilistic Object Detection Challenge. Now, we are actually lucky enough today to have all 3 representatives of all 3 of these Probabilistic Object Detection Challenge papers. So I'm also going to take a quick tangent to just quickly mention the Probabilistic Object Detection Challenge and to present to the representatives of that challenge their digital certificates. So the Probabilistic Object Detection Challenge, again, big thank you to the prod team that was that created the Probabilistic Object Detection Challenge, members both past and present. So this is an excellent group of people to work with from the Robotic Vision Challenge team. This year, this was the 3rd iteration of the Probabilistic Object Detection Challenge. We've got 39 registered participants, about 15 new submissions across 3 different teams. And I would like to send my personal thanks to everyone who registered an interest in the competition, and in particular to celebrate the 3 finalists in the competition. So in 3rd place, with the paper Probabilistic Object Detection via Deep Ensembles, I would like to thank you very much for your contribution. And today here we have Zongyao Lyu to answer questions about this paper. So big thank you to the entire team for their contribution. In 2nd place, there is the team with EPROD, Evolved Probabilistic Object Detection with diverse samples. And a big thank you to that team, and the representative on the panel here today will be Sungwook Lee. And in 1st place, a big thank you and congratulations to the paper Probabilistic Object Detection with an Ensemble of Experts by Dimity Miller. So big thank you to all of these team members and the panelists who are going to be presenting their teams today. Very much look forward to conversing with you in today's panel, and also to seeing more from your probabilistic object detectors in the future. Okay, with that out of the way, I encourage everyone who is here to enjoy the workshop session, ask all of your questions to the panel in the Q&A, watch all of our workshop videos, read the workshop papers, and hopefully gain some extra insights into how you could improve the way that you go about evaluating your object detectors. and potentially doing some probabilistic object detection. And overall, just enjoy. Have fun with all of the content we've created. If you've got more questions about robotic vision challenges, about the group and such, these are all the various links that you could use to try and get in contact with us. So with all of that out of the way, I'm going to stop screen sharing and finally be able to see all of my panelists at once, which is excellent. Okay, so thank you everyone for being here. What we're going to do is we're just going to go through one by one, so you can introduce yourselves and what your contribution to the workshop was. So we'll go in the same order that we've got you on the workshop website. So Walter, would you like to begin by introducing yourself?
Sure. Hi, everybody. I'm Walter Scheirer. I'm an associate professor of computer science and engineering at the University of Notre Dame. For a number of years, my lab has been working on adapting the methods and procedures of visual psychophysics to computer vision. And so my keynote talk for this workshop covered that material. And if you haven't seen it, I encourage you to take a look at it. But I think I'm going to touch on some of what that is in this panel session and why it's useful for evaluation and object detection.
Thanks, Walter. Larry, would you like to introduce yourself?
Yes, I'm Larry Zitnick. I'm a research scientist at Facebook AI Research. I was one of the invited speakers. I guess I've done a lot of work in data sets for the computer vision community, including COCO and VQA, and more recently looking at some applied applications such as speeding up the acquisition of MRIs, et cetera, which also required a lot of data set acquisition as well. So I've kind of been haunted my entire career by mistakes and the challenges of creating large-scale data sets and the repercussions of doing so. So looking forward to chatting about that today.
Excellent. Thanks, Larry. Sungwook, would you like to introduce yourself?
Hello, everyone. I'm in South Korea, and I'm in master course at computer vision task. And I am interested in apply on real world, the object detector and segmentator. So thank you.
Right, thank you, Sungwook. Looking forward to hearing more from you. Zongyao, would you like to introduce yourself?
All right. Hello, everyone. So my name is Zongyao Lyu. I'm a first-year PhD student from the Department of Computer Science and Engineering in the University of Texas at Arlington. And this time I participate in the probabilistic object detection with two of other our lab members. And here I want to learn from other teams and try to get some more experience. Thank you.
Thank you. Thank you for introducing yourself, Zongyao. Dimity, would you like to introduce yourself?
Hi everyone, I'm Dimity Miller. I'm doing my PhD at QUT in Australia, looking at uncertainty from object detectors. And for the workshop, I participated in the Probabilistic Object Detection Challenge. Very excited to be here.
Lovely. Thanks, Dimity. Felippe.
Hello, everyone. So my name is Felippe. Glad to be here with you. I am a control engineer, and currently I'm working as a research engineer at Fraunhofer IKS in Munich, Germany. And my research is basically about certifiable AI and also robust intelligent systems. And with my colleagues, we submitted a paper in this workshop that is basically about comparing some different merging strategies for a deep ensemble setting and how it also impacts the uncertainty estimation task. Yeah, so that's it.
Cool, excellent. Thank you, Felippe. And Rocio, would you like to introduce yourself?
Hello, everyone. I'm Rocio Torres, a PhD student at Politecnico di Milano. And I participated in this workshop by presenting a paper on a tool that allows us to evaluate how the model performs under different characteristics of the objects in the data set. So by providing meta annotations and evaluate how the model performs based on these different values of the meta annotations. That's it.
Cool, thank you very much. And then the only other two panelists we have are Niko and myself, organizers of the workshop. We're part of a robotic vision challenge group here at QUT and the Australian Centre for Robotic Vision, and QUT Centre for Robotics as well. Got to remember all of the institutions. And very much interested in the creation of challenges, benchmarks, etc., that allow us to quantifiably analyze robotic vision systems, which is an issue in our field of research. Okay, well, now that we have the introductions all done, unless Niko would like to say a few words about himself as well. Sorry, I completely.
Oh, that's fine. I think you summarized it.
Cool.
Quite well.
Thanks. All right, so we may get started. So we've got a few pre-written questions, both on our Slido page and that Niko and I have created ourselves. If anyone participating in the audience has a question, feel free to use the Q&A functionality to pop a question there, particularly if you've got any specific questions for specific panel members, and we will get to them in the fullness of time. This is supposed to be an interactive session, so try to be an active participant. All right, so we'll start off with a nice general one, I think, which is on the broad scope of this workshop, which is very much the question of if we consider our norms for object detection evaluation as data set, apply your algorithm to a data set and then get some mAP derivative out as your evaluation measure, what potential flaws might there be in such a system? Are there any weaknesses that people as a general community should be aware of that limit how useful this particular representation is? I would open the floor to people. Maybe start, Walter. Would you like to take a crack at this?
Sure. So I think one of the big limiting factors for this particular problem, and really for the field at large in computer vision, is the reliance on summary statistics to really give us a definitive answer as to whether or not something works. In many cases, a summary statistic will bury the failure cases, right, the individual failure cases, and you won't have a good sense of where the system is going to break down in operation. And so that, I think, really needs to be questioned more than it is, because we do have a lot of real challenges in computer vision, especially when you're applying it to robotics, right? You know, why can't I buy a safe self-driving car in 2020, right? Everybody told me I'd be able to do this, right? Like by now, but it's not there. And I think part of that claim came from this idea that we're doing so well in the data sets and the summary statistics are great, right? That means we're solving the problem, when in practice that was not true.
Cool. I open the question up to the rest of the panel. Would anyone like to chime in with their opinion?
So I guess the point you're making is that we're also burying what we could learn, right, from these failure cases, because we don't actually look at them as much. We just care about the number at the end, but we don't look.
Yeah, absolutely. Yeah, I mean, if you have, say, like a very high accuracy score, right, on a data set, you're saying, great, you know, it's like it's close to ceiling, I've solved the problem. But what if all the failure cases pointed to like a very critical problem that was just underrepresented in the data set, right? Like there could be a bigger issue lurking there, which is ignored.
Mm-hmm.
I think one of the fundamental problems is that the evaluation metrics are kind of, well, they're built based upon where the community is when the data set was created. So, you know, that's why you use, you know, IOU of 0.5 and, you know, mAP and the COCO AP. It's like, those are great measures for when the data set was created. However, Now that like algorithms are working a lot better, et cetera, you probably need to update the evaluation metrics. We shouldn't be looking at IOU 0.5 anymore. You know, we should be 0.7, 0.9. And then the other thing is, which Walter, you already mentioned, which is these evaluation metrics are useful for some applications and terrible for others. Self-driving cars, they're meaningless because you need to know how many times you don't find the human, right? I mean, that's what matters. So I think there, you know, you need to look at, you know, in some applications, false positives are important. Some applications, false negatives are important. It really becomes application specific in this case. And I think one of the questions might be is how to expand the evaluation metrics on a data set such that it can, you know, broaden the impact for these more realistic applications, for like robotic applications and, you know, self-driving car applications, and not just like image labeling applications, which is what I think a lot of the current data sets metrics are more geared for.
As a follow-up to that general idea, then would like we've got as one of sort of the pillars of computer vision is the general task of object detection. Is the sort of general task of object detection now too broad? Do we now need to sort of go into our specialized fields, do you think? Because there is this issue of what does it get used for? If the goal is just to, you know, beat a data set, then that's great and all, but that I don't think that gives us much in the way of what where we want to move forward with object detection. It's surely going to be used for something. Are we at the stage now where we're okay at generic object detection, but we should start looking at these more specific problems with their own evaluation procedures, potentially?
I want to give that a lot of thought before going in that direction. Mainly because from what I've seen is that approaches that work in one application generally work really well in other applications as well, right? And you want to show the generalizability of the approaches, you know, that we're building. Unless we end up reinventing the same thing for different applications, and then the field gets really messy. So you want to keep the field focused. The question is, you need to focus them on the right problems. And that's the reason why you see one data set supplanted by another. You know, it's why we started with, you know, Caltech 101 and went to ImageNet, or with Pascal and then went to Coco. And ImageNet and Coco are getting along in the tooth right now. It's probably time to, you know, I hate to say retire them, but, you know, we need to look at what's beyond them. You know, for instance, like the Elvis data set that Ross and others generated, looking at low shot learning, you know, few shot learning, that sort of thing with a long tail. I think other ones that might be more applicable to self-driving cars could be useful now too, you know, or that are more, you know, tracking oriented, you know, that sort of thing.
That's a good point.
So Rocio, in your paper, you proposed a diagnosis framework, right? Was that also guided by this idea that we don't just want to bury everything under one number, but look into the failure cases and learn a bit more from what's happening and when it fails?
Yes, exactly. The idea was to actually, when we work in applications, we really take a look at the cases we are not working okay, because that's the important thing. And in some applications, it is critical to understand, okay, I have a 90% accuracy, but if that 10% is critical for some reason, then I want to take a look at that. And the idea is to like split the analysis into, for example, we work in some tasks with remote sensing for detecting illegal landfills in Italy. And in some cases there are objects that are critical in this case. We are still we are creating the data set with experts in this field. We want to really understand from the experts on the field what are the characteristics of the objects that are of interest and which are more critical. So the idea was to understand how the model performed when we have an object. These might have different characteristics. For example, if we are working with satellite images, we might have the point of view or the weather conditions of the acquisition of the image, or I don't know, of course, if the object is large or small, so we want to split the analysis for the object, not only for the mean average precision of or any metric that you want to use on that specific object, but also split to understand which conditions make it more difficult. For example, if we are, as I said, we have the weather acquisition conditions of the images. So to understand how much impact it has, the weather, on the READ, because one might think that okay, with haze it will be more difficult to find a certain object, but maybe that is not the critical case. So the idea is to analyze that, and also to understand that, and also we have analysis on the false positives. So to understand, for example, if the major problem is that we are confusing the object with another object, if we have similar categories, or I don't know, if we have a localization problem because of the bounding box, or the idea is exactly that, to go in the cases that we are not working very well, to understand why, and maybe we cannot improve, maybe we can, maybe we don't know how, but the idea is to really understand what is going on in our model beyond only one number that says it works okay, because maybe for the experts in the field that we are working to create a model for them to use, it's not enough that we say it has a 90% accuracy. They really want to understand which are the cases that we are not able to find. So to provide some input on that, and to really explain if they can trust in one case or in the other. So yeah.
Thank you. On a potentially related note, Walter, your stuff is very much on use of psychophysics, and you look a lot at robustness of systems, and you're very through your talk there is a lot of talk basically about testing the systems until they break, but at the same time still making sure that they are something that a human is still able to understand. And you only have a couple of cases where there's sort of a superhuman type performance. Do you reckon that moving forward in the analysis of object detectors in particular, that we should always be including a human in the loop in some way of the evaluation? Because you have lots of comparisons to what a human is able to see and understand. Should the human comparison test always be there when we're looking at an object detector and what it's able to do?
Yeah, that's an interesting question. I'm not sure I would say always, because it's expensive to get human data points exhaustively, especially for some types of evaluations in computer vision. That said, if you have a set of methods and procedures where you can perform a consistent test, right, between a computer model and a human, that's really useful. Right, computer vision plays fast and loose with claims about human or superhuman performance. And usually when those evaluations are done, they're not done in a way that's consistent with what is accepted practice in psychology, neuroscience, right? Other fields in vision science that do these types of tests. And so, yeah, I mean, if you can do it right and if you can bring it in, I think then it becomes very illuminating. Because in some cases, like we have found, certain computer vision systems are, superhuman, like in a psychophysics regime, which is quite interesting, right? As we could really falsify those kind of claims. In other cases, when that claim has been made, it's completely bogus, especially when it comes to things like object detection. That is still a really, really tough task. Where we see superhuman performance is usually in tasks like face recognition in a very, very controlled setting, right? Where you don't have a lot of confounding factors.
Cool, thank you.
Yeah, I found it quite interesting. Larry, in your talk, you were talking about the streetlight effect and how the community tends to investigate problems that are sort of easy to measure progress in or to evaluate, and how evaluation metrics and data sets sort of lead the field in a certain direction. And I was wondering, when I saw Walter's talk, if doing evaluation more on with these psychophysics methods, if that would sort of lead us into one of the problems that are currently in the dark, where nobody really looks at because we don't know how to evaluate it properly. So I wonder if that could lead us into some really interesting and also practically more relevant
It's
these
an
abstractions?
interesting question. One thing that's come up a bunch that we haven't been able to put our finger on, or something that we've been debating literally for years now, is what is the human accuracy on Coco, for instance. It's a really hard thing to measure, because is it a human that's paying attention? Because a lot of the objects are small. Is it when you get 10 humans together and you take the aggregate voting of all of them? When the 8 or so original Coco members, what we did is we actually labeled images ourselves to see how consistent we were in labeling the images, and we weren't that consistent. And we were all computer vision people. We're all looking at the images really hard. I remember Pedro thought something was a mirror, and I was like, that's not a mirror. And how do you label a banana? Is it a single banana? Is it a bunch of bananas? There's all these different things that is really hard to nail down in a consistent way. And that's something that I think is really, and I think it's something that's missing in our evaluation metrics. Back, and you go to your point, which is, this ambiguity, the distribution over possible answers potentially, or, human-like, how do you, measure something like that? That's tough, because we always want things to be exact in our field.
Definitely. Though I would argue. Sorry? There you go, Niko.
Yeah, I was just saying, I also want to encourage the other panel members, if you want to chime in and ask questions to each other. Yeah. It's not just us asking questions. That would be good. Yeah. Does anybody want to?
I'll just add one quick point, because I think Larry raises a really interesting question. What if you can't get consensus, right, for a labeling task? What do you do? A number of other fields working on machine learning have looked at this, especially like the KDD community. There's a lot of work on rater reliability, Bayesian models of rater reliability. And that's stuff I think I would love to see if we did more of that, because computer vision is really fueled by those labels. And it's troubling when we only use one person per image, right, to do the labeling. This is a great point.
Yeah, it'd probably be good if we had sort of uncertain labels plus uncertain detectors, because the whole concept of the probabilistic object detection challenge, for instance, was that a computer vision system is not likely to be precise, down to the pixel level anytime soon. Yet at the same time, with our evaluation procedures, we are always going, yep, a box, that's the perfect representation. It's definitely within that box. It's definitely here. So as potentially an attempt to segue, I've got a question for the probabilistic object detection panel members, which is very much how important do you think the concept of probabilistic object detection actually is? Is it a nice niche subject, useful only for roboticists, or do you think it has potential broader implications? Where do you use it within? Where do you see it within your own research? Zongyao, would you like to give that one a crack?
I'm sorry, can you repeat your question?
Yeah, sure. Is probabilistic object detection a niche novelty that's useful only for roboticists, or do you think it has potentially broader implications? And where do you see yourself using it within your own research?
Actually, this is the I put the question question like this in the slide also. Basically, I'm new to this area, and I just participate this time in the challenge as a start of my research. And I have read a few papers, but there are some fundamental problems that I didn't understand very well. So like there are some uncertainty estimation methods that published the recent years, like the dropout and the deep ensembles and etc. So, actually, yeah, I'm always thinking. So the uncertainty estimation that used in the computer vision, especially the object detection. So this combination, how can this combination really helps helps in practice for the object detection task. So yeah, this is something I didn't understand very well.
Do you want to take a crack at that, Dimity?
Yeah. Zongyao, so you're asking how uncertainty in practice helps object detectors? Is that right?
Yeah, basically that's it. Yeah.
Yeah, I think so. Where at my uni, the labs I'm working in are all centered around robotics and really applying computer vision to some real application. And we always have this problem where we're using stuff that's trained on a data set and then applying it in some slightly different environment. I guess the problem there is you can't always guarantee what you're going to see or guarantee that you've got the same testing conditions as you had for training your object detector. And the idea then with, if you had a reliable uncertainty, is that should kind of alert you to when you might fail in the object detector. So if you have a robot or even say a self-driving car that has to detect pedestrians or something, hopefully with an uncertainty, you would see if there was an error kind of in the classification of the object detector, for example, you would have a high uncertainty and that might inform your actions on a robot. So you've got a high uncertainty in your perception, maybe then you're more careful with the actions that you take, which might have, I guess, important consequences.
I would also say, like, we very much focus in robotics here because that's sort of what we do. But it was also quite fascinating in Felippe's paper when he showed that there was more of a direct correlation between the variance of uncertainty with regards to spatial uncertainty to actually being able to determine what a good object detection should be. So that that plot of yours, when you looked at label confidence and label score versus positional variance, was quite fascinating, and I really enjoyed seeing that. So would you like to talk a little bit towards what it is that you'd found there?
He looks frozen.
He does look frozen.
Yeah. Oh no.
Online is perfect. we may let Felippe get himself sorted. And then
maybe before he comes back. So I think Dimity just raised an important point about this whole issue of basically open set problematics, right? Where we apply something that has been trained under certain conditions, but then we test it or deploy it under different conditions, and suddenly things might go wrong. And Walter, you did some early work on open set recognition, and I was wondering, can psychophysics help us on that front as well? How do humans even react to open set conditions, or is there such a thing for humans?
Good question. So the answer is yes. In fact, my lab is doing this work right now. There's a large DARPA program running in the US called SAIL-ON, which is looking at this question of open set, open world recognition. And what my lab is trying to do is basically understand the human perception of novelty, right? And this is important because some samples are more difficult than others, and it'd be really nice if we could characterize that information and be able to understand what may be easy or hard, right, from a modeling perspective. Again, this is something that I think is really understudied when it comes to computer vision in general, and something that I hope will help us as we move forward, right? Especially when you think about like open set and novel inputs, how far are they from what we know, right? It's like, where do you draw those decision boundaries? Where is there confusion? That tends to be the important part, right? You want to account for in your model. And understanding the human perception of that can clear some of this up. But it's a tough problem.
Probably more to the probabilistic object detection challenge people. We in the challenge focus on the spatial and label uncertainties, But as mentioned before, open set detection is not really considered within such a challenge, even though it probably should be, because there's a bunch of objects within the scene that we don't actually know that we don't know what they are. And frequently the type of error that we'll see is that we will put a box around something that looks vaguely similar but is technically a different class. Is open set detection something that should be considered for a challenge that purports itself to be probabilistic object detection? Or is that a step too far?
I think there almost is stuff in the challenge data set that is open set objects. Like it's just the nature of it, the stuff that you don't have labeled but actually is an object, like the bathtub, I think, for example, is an unknown class. And that might get detected.
Keeps getting classified as sink.
So kind of, yeah, and then I guess the problem then is whether you want the detector to ignore open set objects, so you don't want them to detect it, or if you want it to be detected as a detection, but have a label that says unknown. I guess in the current setup, it's preferable to just ignore the detection, whereas maybe in applied applications and stuff, we might actually still want to detect that object and say there's an object there, but I don't know what it is.
Sungwook, do you have an opinion?
Pardon me, what is the question?
The question generally is, should a probabilistic object detection challenge where we're caring about things like label uncertainty, should it attempt to also include open set object detection as a challenge because of the uncertain nature of object detection?
Firstly, I think in OpenSet there is no unseen classes a lot, so object detectors should be careful about overconfidence in unseen class. So we should do running object detector more discriminatively, seen class and unseen class. So in this case, we should do pay attention to running the metric that discriminate seen and unseen classes in feature domain. So I think in these cases, I think is uncertainties of other is very important in this case.
Thank you. Zongyao, did you have anything you wanted to add to that, or are you pretty happy with the responses thus far?
I'm fine.
Any questions from?
From you guys is because when you think about open tasks or open classes, is which tasks are you interested in? Is it obstacle avoidance? Is it grasping? Is it am I going to get hit by something? That sort of thing. Because if it's one of those tasks and you can figure out a way of scaling the evaluation of it, it can get really interesting. But I think one of the big challenges in a lot of these tasks is actually scaling the evaluation, so in a way that you can make it repeatable and scalable.
I think, if you're asking us, I think we are always thinking very broadly, right, in lots of different applications in robotics. For instance, the domestic service robotics, right, where you have like a lot of household objects. Every house would be different. Robots would have to adapt to very different environments very quickly without any, big burn-in or learning phase and all these things. And I mean, I guess the consequences of making open set errors could be a sort of trivial. Maybe it's an annoyance, right? But it could also be catastrophic or at least damaging. And then, of course, if you move to self-driving cars, it could be catastrophic. So I think there's a lot of different scenarios where it really matters. And ideally, I'm always thinking of it that you want to propagate uncertainty all the way from your perception through your world modeling, if you're thinking, semantic SLAM, object-based SLAM, all the way through to the decision making and to the action. So you ideally, your distribution of actions that the robot wants to take in a certain situation should reflect the uncertainty on the perception part of it. If this chain is broken somewhere in between, I think that always leads to strange side effects, or it's not, I don't want to say verifiable, or there's nothing with guarantees or verification along these lines, but at least it's less safe, I think, than if you would have this this chain all the way through. Felippe, you're back.
Yeah.
Yeah.
Do you want to loop back to that question? Did you hear the?
Yeah, of course. So apparently things don't work so well in the middle of the night here, but. So the question was basically about this confidence versus variances as a good estimation. And maybe I can also go back for the previous question about how uncertainty helps on practical cases. So I can also talk something about that. Because here at our institute, basically we are working with safety people. So it's more about safety AI or safety in general. And safety guys, they always want some hard proofs that things gonna work as they expect. And it's difficult to argue with some AI-based models. And usually, for example, if you have these confidence estimates, people are like, okay, but what does that 0.9 means for us? It means that out of 10, 9 times you're right or not. And all this calibration part also, because those values are not actually well calibrated. And so uncertainty is helping us trying to sell, let's say, these AI models as something more reliable, because if you have these uncertainty estimates, and they of course are also well calibrated, it could help on trying to embed this on some more critical, safety critical systems. And yeah, so one of the things we wanted with our paper was to see if these mainly used confidence scores or softmax confidence scores were as good estimates for the quality of the bounding boxes as the uncertainty estimates. So this was one of the points of the paper, and we found out that actually the uncertainty estimates looks as something better to get the quality of the bounding boxes, and should give a better idea of if there is really some object in that place or not. And yeah, basically that's it.
Now, I found that a very interesting paper when you were looking at the label scores not really being that well correlated to positional accuracy, because that's what we use all the time. Yeah, like we've got NMS where we're going, oh, we're more confident that this this box here is telling us that it's a cat, and we go, that one must be the most accurate box. So I found it very fascinating that you were seeing with your ensemble tests that wasn't necessarily the case. One small follow-on I would potentially add to that is the question, did you try playing around with those variance estimates when used for NMS, or was it only for looking at the outputs you got from ensembles?
Yeah, we did not try for this paper, but it's something we are also working here with, because as you said, it's interesting because mainly they use these confidence scores for NMS. So even though they should be only related to the classification task, they're used also to select which boxes are overlapping the ground truths or not. And yeah, we are also playing around with these ideas of integrating the variance into the NMS part, but maybe in a future paper we can release some results over there.
Oh, very cool. Interesting to something to look forward to. We have a general question. Yeah, a question in the Q&A. Yeah, I got it.
In the Q&A. Yeah,
it's a really fun, long question.
Yeah, so Marek, thanks Marek for asking a question here. I'm going to read it out. I don't know if the other panel members can see this. The question is, could you please comment on the following paradox? We all need common databases, like a /data sets, if not for training, at least for testing. And building these data sets is expensive. However, once the database or data set is released, we all start being biased towards it. So I guess the whole field, maybe over the years, starts overfitting to it, right? Could this be resolved, like having a gold standard that's useful for many years, at the same time being flexible and evolving, so it does not hurt development in sensor technology and theoretical models? Also commenting on the COCO challenge in object detection, apparently had scores worse than in 2019, which is maybe a sign of saturation. Yes, thanks for the question, and please, panel members, feel free to answer.
I could talk for a while about this.
Mm-hmm.
You know, it's funny. There actually are a lot of things you can do to make a data set have a longer shelf life and have it more useful to the community. But one thing kind of pops in mind at the very beginning, which was, you know, what not to do and how you can hurt a community. I think a good example of this, for those of you who might be familiar, is a Middlebury stereo data set, which was like 4 examples of pairs of images, and they had ground truth disparity or depth information for these images. And when it came out, it was amazing because we could finally compare one stereo paper to another. Before that, you had no way of directly comparing these papers to each other. So this was huge. It really like drove a big stereo vision wave in the early 2000s, including myself. I was working on this problem. But then in hindsight, you look back at it, and I remember you know, memorizing almost every single pixel in those images, knowing exactly where the disparities go wrong. I'd overfit to the test. I mean, it was all test set and training set. So, I mean, there's no models that you're training for this. It's all like hacking it together. So you overfit to it. And then you mentioned, you know, not hurting sensor, you know, development technology. Like it was so contrived, this data set, because it was just 2 images, or most of the data was 2 images. Why not take 3? I know humans, we have 2 eyes, we want to do the same thing as humans, but you know, take 2 images, or take 3 images, take 4, take 5. Like they're free. Why not do it? And it's one of the reasons why I ultimately stepped away from the field, because I felt like it was a academic problem without any real world impact. Sorry, anybody who works in stereo vision out there. But in any case, that's a great example of looking back in hindsight, it really helped the community, but it ended up hurting a lot as well. Now, when you think about, you go to today and you say, okay, how can I make a data set that actually is going to scale, going to be a gold standard for 4 or 5 years, et cetera? I think this comes down to putting a lot of work into it, which is understanding where the field is now. You want current algorithms to get 10 or 20% accuracy on the data set that you're creating, not 80%. So that way there's room for improvement. It's really important that you create a test set that's very diverse with difficult examples which go beyond what current technology can do. You want to push the field in new directions. Like in COCO, we went from bounding boxes to segmentations, which I thought was huge. The data set was very diverse. And then also setting up test servers. This seems like a small thing, but basically don't give away the test data. You give away the test data and people are going to overfit to it. So make sure that nobody has the test data and that you restrict access to the test server so that way people don't overfit to it. So those sort of things can be really useful. And the other thing I've seen is for more practical applications. For instance, the Fast MRI project is we've been having yearly challenges. And what we do is we change the challenge each year to kind of go with the field. So we reconstructed a certain type of MRIs the first year. The second year, we're going to expand so that way it becomes a harder problem. You do different types of MRIs or using different machines, et cetera. So through the use of workshops and challenges, you can kind of nudge the field as well. And when you create a data set, you need to think of basically 2 leaderboards. One leaderboard is a leaderboard that everybody submits to for papers, which has the same data year after year after year. So that way you can always compare against like all the papers that have been published in the field for like the last 5-10 years. And then you have the challenge leaderboards, which are basically updated every year with new data and, you know, kind of pushing the field in new directions. So like you can look at it as both, and both of them can be tied together. But at the end of the day, all data sets need to be retired. And it's at different rates. Like Clever probably could have been retired about 6 months after we released it. VQA needed a new update because it was too biased at the beginning. Coco is probably reaching the end of its life right now. So, you know, it really depends on a per case situation and how the field moves.
What would you say is the
notion of?
Oh, sorry.
Yeah, you go.
Yeah, thank you. What would you say is like the main sign of a data set needing to be retired? Because like we're not getting near 100% on Coco yet. There's still obviously some issues there, but we are sort of saturating. Is that saturation enough to say that it's done, or?
It's not, when you say a data set is saturated, it's not that you're hitting 100% accuracy, because on a data set like Coco, you're never going to get there because the labels aren't accurate. I mean, there's a lot of like missing, you know, labels and, you know, a lot of false negatives, false positives, all that sort of stuff. What you look for is when basically all of the papers written on it are algorithm plus papers. Like there's nothing new, nothing novel coming out of it. I remember in the last days of Pascal, we looked at a lot of the algorithms, and it was basically deformable part model plus papers was all that was coming out. And you felt like the field wasn't really going anywhere. I think with Coco, you know, RCNN variants, you know, tons of variants of it, but we kind of explored that space pretty well, right? And if you want to push the field in a new direction, you probably need to we need to change direction in some way or not. So I think that's what you kind of look for, is like, am I excited about the papers? If you go for a couple years and you're like, I haven't seen a single paper that like gets me excited, it's probably time to create a new data set, in my opinion.
Oh, cool, thanks.
Can you share some thoughts on what you think the new exciting directions should be that are currently in the dark, where we don't have a street light shining there?
It's tough because, to be frank with you guys, I've taken a detour from computer vision for the last year, and I'm working on a new project, which has nothing to do with computer vision. So maybe that says something right there, which we haven't made public. It'll be public in a little bit. You know, I would say, you know, few shot learning is a big one. You know, that's one of the reasons, you know, when you have a small number of training examples, I think we just totally are ignoring that. When you have situations like the car, you know, the self-driving cars where you need to recognize things, you know, 100% of the time is super important. 3D, basically, I would love to find a way to evaluate in the 3D world, whether that's through simulation or through actual 3D world. Like, if we are to get out of where we are right now, we need to figure out a way to tackle that problem. And I think it's going to be through simulation, but it needs to be done right, and it needs to be done in a way that we don't, like, there's only like 10 simulated environments and we ever fit to them all. You know, so I think that's a huge challenge for the field. It's kind of like dialogue in an LP. Dialogue's really hard to evaluate because you can only do it with other humans. Like, and that's kind of really hurting that field in progressing. So I think here, whenever you have interactions are expensive, whether it's in the real world or with humans. So if we can figure out a way to get beyond that, I think we'll be a lot further along, especially like the assistive robots that you're mentioning. You know, we need a way to make that repeatable and scalable.
Anybody else wants to chime in on these points?
One quick thought, I wonder if we should, I mean, not stop using data sets, but also use, I don't know, real inputs, like do more with the real world. I think Larry's hinting at that with the simulation environments. Again, like thinking about OpenSet especially, like we end up with these closed universes, which are very, very small compared to the real world. And again, as I pointed out at the beginning, that's kind of sort of misleading, right? Once you beat the data set, you think you solved the problem, but you really didn't. All you did was like vastly undersample the real world. And so data sets certainly have their purpose, especially for training, right? I mean, we need some data for a data-driven model. But again, I think I'm probably preaching to the choir with all these roboticists who are on this Zoom, right? It's like roboticists know what's up, you know, they know the real world and they get frustrated with the data set game. But I think there's room for both. And I'd like to see that, you know, in more common practice when it comes to evaluation regimes across the board in computer vision.
Yeah. It's definitely frustrating, but at the same time, we in robotics, we're also slightly envious of the computer vision community in that you do have the ability to compare so easily. Because that's one of the things for the robotic vision challenges is that we've just not had that. There's been a lot of people going, I've got my system, it works on my robot in my lab, therefore it works. I've got my system, it works on my robot in my lab, therefore it works. Having the ability to compare has not really been something we've been able to do until fairly recently. Outside of probably Kitty is the main one that we are able to really use and reliably test against. But even that's probably very saturated by this point because of the amount that we focus on Kitty. So
Yeah.
One thing to think about here is if you go to the dark ages, before 2000, almost all you had there was a ton of, and people worked on object recognition then too, right? And the way that you wrote papers back then was you would come up with a cool algorithm, a cool way of solving a problem that you think would work. You write up the algorithm, and then you find data that it works on, right? And you can't go online. You can't search the internet for images because it didn't exist. So you go around taking images yourself and try to cobble together a data set, that sort of thing. And basically, we weren't going to make progress on object recognition until we could get the data, until we get a large number of images. And I think for robotics, it just might be the same thing, just 10 years later. Like, we're not going to make any progress on robots in the house until we have robots in the house. Just like we're not going to make, a progress on object recognition until we have cameras in everybody's hand, and you can easily grab, 1 million images off, online with labels attached to them. So it might just be a waiting game in some sense.
And it is quite interesting that maybe since, I don't know, 12 months, right, there's a number of initiatives around the globe, and like Dhruv Batra, I think, is leading one of those as well. And we are doing something similar where you have basically a room and you have a real robot and you can upload code and it does a task on the real machine in the real world and then evaluates it and tries to basically bridge that gap from doing something in simulation and then having a similar or even the same setup in reality and then evaluating there. I think that's super exciting to see, and seems to be like a bit of a converging idea that multiple people around the planet had at the same time, which is great to see.
Yeah, I think it's really good to see those advances. There are people working in that direction, because the simulated environments are great for the visuals, but it seems like the physics you'll never model correctly. It would be really hard to model the physics correctly.
Okay. Any other questions from the panelists to the other panelists?
I have another general question. You go for it.
I have a question for general task. Even if instance segmentation takes more accurate works, why need we object detection with bounding box? I wondering your opinions.
If we can avoid just using a box, I'd prefer it. I see, like, personally, I see bounding boxes as that wonderful, like, first step of going, like Larry said, the state of what we're able to do at the moment, first step of going, where generally is this thing exist? But if you're actually going to try and use anything, particularly for oddly shaped things that don't fit well inside a box, segmentation, I'd say, is much more direction to go. In my world, I would also say probabilistic object segmentation would be more the way to go. So you're not just saying this pixel definitely has a cat in it. We're just saying probably the cat's in this general area. So yeah, that's my thought.
We debated dropping bounding boxes completely from Cocoa, but we ended up keeping them just for backwards compatibility, because that's what Pascal did, and we basically used the bounding boxes, and people already had code for that as a stepping stone to get people interested in the instance segmentation. So that was more of a, how can we get people to adopt the new data set who aren't interested in instance segmentation. So it's like that stepping stone for the community to get them further along.
Thank you for your answer. Thank you.
That being said, we still see a lot of just bounding boxes and even bounding boxes being evaluated with just like 0.5 IOU. Do any of you think that we have gotten into a bit of just a rut of tradition where, oh, this is the way that we do things, this is how we evaluate things. If we're not evaluating it this way, then what do our numbers even mean? because I found when trying to make the robotic vision challenges and the concept of probabilistic object detection, evaluation measures for it, etc., all the reviews were just sort of going, well, yeah, but does that mean that all of our numbers are wrong now? And it was sort of hard to convince people that maybe just a different perspective is all that was needed. Does anyone here think that, like, perhaps we are in a rush, and if we are, how do we get out of that?
That's a very good question and a very tough one. I think you hit the point correctly. There's an expectation when papers go into review to compare against something, right, beforehand, and right, you want those things on a consistent basis. And so we just get stuck on that same track, yeah. Like IOU at 0.5, right? That's just, it's going to be with us forever now. It's going to be very, very difficult to change that.
If you can create a bridge, that would help a lot. So what you want is for people to report on the old metric, but then say, oh yeah, by the way, here's the new metric. And then more people do the new metric. And then before you know it, they can ignore the old metric and only report on the new metric. But you can't do that in a big step change generally. That's a gradual transition that happens in the community.
Definitely. I guess
just as well, I think it, oh, sorry. I think it can be hard as well when you're introducing something so new as a way of evaluating things. If you notice that everything that's kind of been done so far is so bad at it, it makes it really hard to kind of like make, I guess, progress, because you're kind of stuck at zero and it's like, oh, was all of this for nothing, you know? So that can make it challenging, I guess, which I guess makes sense with what Larry was saying, how you have to make it a gradual thing where maybe you can transition.
That's why they picked 0.5 IOU, because that's not the metric you would use if you wanted something to be practically useful. They picked it to make the algorithms look reasonably decent at the Pascal dataset. So, you know, for your work, it might make sense to, you know, just pick a threshold that makes things look better, at least initially.
When you introduced the COCO and also the VQA datasets, were there any points where you had to, you know, change things, or you thought, oh, this is probably good, but then the community said, no, this is too hard, or that doesn't work for us, and did you have to backpedal and make changes?
Yeah, well, the COCO one went through a year or two debate amongst 10 plus people and talking to the greater community about it before we actually launched it. So that went through a lot of iterations, and there's a ton of different points in that about why we ended up with the design decisions that we did. I think an more interesting case is actually the VQA dataset, because the VQA dataset was created explicitly because we screwed up on another dataset released just before that, which was the image captioning dataset. So we released the image captioning dataset without baselines, without evaluation metrics, and we just released the data, and it created a total like disaster in that a bunch of papers were released on it, everybody bragging about how great it was, and no consistent evaluation amongst those algorithms. So then we went back, we did consistent evaluation, and then learned that the evaluation was not reliable because it wasn't consistent with what human judgment would provide you. So basically we had, you know, let out a data set which created a new problem that people were excited about that you couldn't evaluate on, and you had no way of telling if somebody's algorithm was better than the other, right? So it's not a good place for a field to be in. In response to that, we said we need a different like language plus vision task, and that was VQA. And we figured that one at least you can evaluate, because the answers were 1, 2, yes, no, black, white, you know, etc. You know, so it's easy to tell if you got the answer right or not. So it seemed like a slam dunk to create that data set and, you know, ship it out. It was a lot of work, you know, and a lot of money to create it, etc. Even with that, we still did not do it perfectly because the data set was very biased. And this is something that Walter, maybe you could have shed light on us by doing human studies on it. But what we should have realized is that if you ask a question like, is there a water bottle in the image, the answer 80% of the time or 90% of the time is yes. Because somebody wouldn't ask, is there a water bottle in the image if there's no water bottle in the image? You know, it's like when you try to guess the answer of a 3-year-old, it's like really easy to predict like yes or no without like actually seeing what they're seeing because, you know, they have these biases. So we had to basically come up with the VQA version 2, or, you know, Debbie and her team and Drew came up with the version 2 of the data set. And I think that was one of the biggest kind of rewrites of a data set that, that I've been aware of, you know, post initial release.
So did you then manually make sure that it's more, that it's not as biased?
What we did is for every image that said, is there X in the image, is we'd find using image similarity scores, we would show Turkers a bunch of other images and say, find an image where this isn't in the image. And then we'd add that to the data set. So that way it was an equal number of yes and no responses. And similarly for like, you know, numbers and that sort of thing.
So as another question of my own in this space, we've got the current paradigm. People evaluate and have some sort of summary metric, and we've heard from a few people now that, you know, that summary statistic is deceptive because it hides so many layers of stuff. There's so much more nuance that you can get from an object detector and an evaluation score. Is a paradigm that we should try and move towards, that people who produce a new object detector should give this more sort of thorough, detailed analysis, and it's understandable that that takes a very long time, a lot of resources, etc., to test that sort of thing. So is it on the person who creates an object detector to try and evaluate it to that level of depth, or should we as a community possibly be more accepting of just pure analysis papers where they just dissect a detector in all ways that it can possibly be dissected? Does anyone have sort of an opinion on that sort of field?
Well, in engineering at large, sensitivity analyses are very common. And that's something, again, we sort of shied away from in computer vision. And again, coming back to my own stuff in visual psychophysics. So for those who don't know, visual psychophysics, it's a way to perform experimentation, like behavioral experimentation, typically in humans or animals, where you choose a stimulus and you choose some variable to control in the stimulus, and you start turning the crank. And you start perturbing that particular condition very slowly, and you keep checking the responses. And eventually you will probably break the system you are testing. And again, this is a form of sensitivity testing, right? So you want to understand, what are the parameters under which this system operates correctly, right? When does it break, and when is it safe? And I think that's sort of essential for so many applications, especially in robotics, right? If this is going to exist in the world with people, it has to be safe. And then that begs the question, where does it break, right? Because the summary statistic is not going to tell us that. So I think that's one basic thing, which again is common practice in a whole slew of other fields that we could bring in. The caveat, of course, is that it's more expensive. That's why people, I think, have shied away from it. That, I think many folks would feel like, oh, this makes my good algorithm look bad. But again, that's not necessarily true. It's just giving us bounds on what the safe operation of that system is.
So these stimulus changes that you also presented in your slides, that's kind of sort of maybe low level effects, right? Like Gaussian blur or occlusions and so on.
Good. Okay, so it does not need to be that, but that's the easy way to start, right? We've been looking at more sophisticated transformations of images using computer graphics. For instance, what if I incrementally add rain in a scene, right? How heavy does this downpour have to be to break the system? We've done other things, like especially with like facial perception, changing the face, right? The different features of the face, right? Different attributes, changing expressions incrementally. All of that stuff can be controlled through procedurally rendered graphics, and you can, right, have perfect control then over whatever variable you're interested in testing.
And can you see a general trend that models who do better under these, conditions then also perform better in a, real world task where they maybe face OpenStat and all sorts of other detrimental effects that you can't really control?
Some of the most interesting, so that's along those lines. Some of the most interesting things we've seen. older algorithms that in some cases are not machine learning based tend to be very resilient to right open set or new conditions, especially if they're low level transformations. They don't seem to be highly impacted, where things that are learned from data, right, these data driven models are basically memorizing the data set. And so if you get a little bit out of that regime, you very quickly break the system. And so I think that is troubling, since so much of this field is based in machine learning. But maybe it's not so bad. We can go back to some of the older approaches in some cases, because they tend to generalize a bit better depending on what transformation you're throwing at them. Does it make sense, right? I mean, I think we all sort of know that overfitting is a problem, but this is like another body of evidence arguing for something beyond just memorizing data sets.
I guess you could also use psychophysics not just as an analysis tool, but also as a basically data augmentation, right? And then
and our lab has done that too. Exactly.
Well.
It's like additional data you can use in a loss function, right? Like, I penalize the easy things, right? Or the things that are easy for humans to perceive more heavily than the things that are difficult.
One thing, just to plant a seed, if you do create a challenge and you create a leaderboard, you can do something really awesome, which is you can store all the submissions that people uploaded, right? And one thing that I think is really good for the community is papers that explore new evaluation metrics. And then what we can do is you can take those new evaluation metrics and you can then run them on all the old algorithms on the leaderboard and then add that evaluation metric to the leaderboard. And I think when you do things like that, especially for problems which are hard to evaluate, I think image captioning is a good example here, where the leaderboard started off with just a couple of different metrics, and then more metrics were added afterwards, which gave like different like ideas for how well the algorithms were doing. And you could do that, after the fact, which is pretty awesome. So if you set up a leaderboard, encourage people to develop new evaluation metrics and actually put those new evaluation metrics on the leaderboard, you can help create like a nice ecosystem, which is like a kind of like self-reinforcing.
That's a very cool idea. I like that.
I like that, because that also sort of ties into the concept that, the big question that we had from the audience before, which was just how do you still keep these standards and continue on. So that'd be very cool.
And another way to look at it too is when you create a data set, it's not just the labels, it's the content that you're generating. So for you guys in robotics, if you're creating videos or like that sort of thing, one of the great things about Coco is that the images have been used for so many other data sets, right? So it's kind of like each of these new data sets, which are created by other folks, are basically adding new evaluation metrics onto it by adding these new labels and evaluating in different ways. And that again helps create that ecosystem of kind of vaguely comparable results and opens up the community.
Yeah. No, because that ties in closely to what I got from Rocio's paper, with Odin just being able to look at all of those different types of metadata that you could just add to an existing data set. One like potentially very specialized question for Rocio then would just be, how do you, like, we've got the data, we've got this idea that we wanted to keep evaluating it in new and important ways. How do you go about choosing what sort of extra metadata that is useful for something like Odin?
Well, in our case, we were thinking like more specialized applications, like, I don't know, you have a specific problem with, in our case, as I explained, we have the experts that tell us what is important for them. So we were thinking at the time is the person that knows the problem, which is maybe more specific, which are the things that they need to look at. And we weren't thinking about a general challenge, let's say, when we thought about this. So I wouldn't know how to respond to which annotations you need to look at, because I think it depends on the problem that you are addressing.
Yeah, very, very much on the specialty track. That's completely fair.
Yeah.
Yeah.
We have a few questions on Slido. Shall we?
Yes, we probably
go
should
to a
go to some
couple
of those.
those?
Yeah.
So there are two questions for Dimity, for the winner of our challenge. The first one is, did you consider the case where the worst performing model is able to detect particular objects, for instance, small objects, better than the others? And how could that be integrated in your ensemble approach?
Yeah, so with the worst performing detector, so just as a recap for anyone who maybe hasn't seen anything about it, our approach was an ensemble of experts, which was basically different high performing object detectors of different architectures, and then to actually associate their detections to particular objects and try and merge them into one detection. We had this ranked association process where we started with the best performing detector, took all of its detections, associated them, then took the next best performing detector, and we ended up kind of with the worst detector with detections that hadn't been associated yet, and we just discarded them, which I think is what the question's getting at, if that's actually a useful thing to do. So we actually did test, and generally adding that worst detector always lowered performance because there tended to be just false positives that remained. I'm not sure if that's something that would generalize to kind of every time you use this technique. I think it worked in our case because the worst performing detector generally wasn't the best at detecting new objects. When it did detect objects, though, it usually had quite a good label quality. So it usually had a confidence score that was fairly well calibrated. So I think that's why in this case it worked, and it made sense to discard the detections that remained because they were most likely false positives.
Thank you.
As a follow-on to that question, Dimity, I had one which was that you highlighted in your talk that the different detectors were good at different things, right? And you were in the ensemble, you were hoping to get the best of all worlds. Did you ever consider weighting specific aspects of object detection differently depending on what the detectors were able to do? Because you said that one of them was better at getting what it was, but not where it was, etc.
Yeah. Yep. Yeah. Didn't do it for the submission, but it was one of those things in hindsight when I was writing it, I was like, oh, yeah. So the detector, it worked out really well. We had 3 detectors. One detector was really good at detecting lots of objects. So it had lots of true positives. Another detector generally had a very good kind of ability to classify objects. So it had the kind of best kind of classification score. And then another detector had the best spatial quality. So it generally had the best localization of objects. And yeah, in hindsight, when we were kind of associating these detections, rather than just averaging them to create the final detection, you would weight more heavily to what that detector's strength was. Yeah, maybe like a weighted average, or even just taking the bounding box of the detector that had the best localization. But yeah, not in this case.
Cool. No, thank you.
I have a question also for Dimity. So how do you see your algorithm scaling up? Because in your case, you're using 3 different models, right? But for example, if you add 5 or 20, would you still only like discard the prediction from the last model, or you think you would do something different?
Look, I don't have a perfect answer for that. I think it would really depend on the performance of the detectors. So in our case, there was like a really clear, if you evaluated each detector alone, there was a really clear drop in performance for the PDQ of the final detector. And that made it very easy to kind of draw the line and only use it to kind of help calibrate the other detectors. But yeah, as you scaled it up, that's a very good question. I'm not sure how you would maybe say, okay, this detector, maybe the worst 5 detectors if you had 20 or something. Yeah, that's probably an open question, I guess.
Could you base it maybe more on like correlation of how confident and how many detectors agree on the same thing, and if a low-level detector is not very confident at all, then you discard that sort of detection, maybe.
Yeah, totally. I think, you know, honestly, for me, the most interesting thing that came out of this sort of approach was that all of these detectors kind of have their own strengths and advantages in performance. And yeah, some of them, you know, have a better ability to localize, some have a better ability to classify. And I think we see like a lot of approaches with ensembling where maybe we're using the same type architecture of object detectors. And I've certainly done that before, and it might give quite good uncertainty measures. But I think we also can get not just good uncertainty, but maybe improve performance by trying to somehow combine, you know, these different approaches to object detectors.
Cool, thanks, Dimity. We have a question in the Q&A that's for Walter. I'll read it out. It may be already discussed, but I have the following question. Walter, I am interested in the problem, how does image enhancement - correction make understandable vision for human eyes by machine learning approach? It assumes for human assistant systems in automotive. Is it possible to show the related research?
Okay, so my group has looked at this question quite a bit recently. For a number of years, computer vision has been looking at image restoration and enhancement. So this is things like deconvolution, super resolution, et cetera. And most of that was for computational photography, right? Make the images look pretty to people. And that's fine, right? And that's why we have really cheap, you know, sensors and cell phones that produce really beautiful looking images, you know, no problem. But the idea had always been floating around, you know, could that stuff make visual recognition better? Historically, the answer to that question has been no. The transformations that are applied in those operations tend to do terrible things to the images, especially when it comes to things like super resolution, because you're often like hallucinating pixels from other sources. These days, big training data sets, and so you could like actually contaminate the feature space. But I mean, the idea still makes sense, right? If I have a poor quality images, there's some way to make it better for visual recognition. So we've been looking at things like joint optimizations, basically try to do image enhancement and restoration specifically for visual recognition. And it does work, but it doesn't work that well at the present moment. And what's interesting, coming back to this question, what you get, the images that have been enhanced, quote unquote, that computer vision models for visual recognition prefer often have really strange looking appearances, like really weird artifacts. But the filters, right, the classifiers, et cetera, in the trained system seem to love whatever that transformation is. So they're not always suitable then for human use. And so I don't know, given like the state of like deep learning for visual recognition, if we'd ever be able to reconcile that. Like, can you make an image that both is enhanced for people and also a recognition model? I think that's an open question. And there's a lot of discussion about that in particular, because it would be nice if you had something that satisfied both, right? Especially if you're thinking about applications in security and defense. Just some thoughts there.
Thanks for that, Walter. Does anyone else in the panel have any questions for anyone else? Ooh. Sorry, Sasagawa said thank you for the question. Answer. Cool. If there are no other questions from the audience or the panel, we may wrap this up a little early. It's been definitely, though, a treat being able to talk to people about object detection evaluation. It feels incredibly niche and overlooked, but to me, it's always felt extremely important that we actually understand what's going on behind the scenes of an object detector. So it's been great hearing some ideas. I hope that anyone in the audience is taking on board some of this sort of stuff. If you are going to create your own object detector, if you're going to be analyzing exactly what you're able to do, or make some claims about how your detector will operate in the real world after seeing its performance in a data set. Perhaps you'll give it a second thought. And yeah, and thank you very much to all the panel members.
Yeah, thank you very much for joining us today, this morning, tonight, whatever it is in your time zone. It's been a pleasure. And everybody who sees this as a recording or in the audience live, if you want to know more about this, the challenge and the papers that were submitted, they are all at roboticvisionchallenges.org, or you can click through to the workshop website there, find some information there. And there's also a little sneak preview on a scene understanding challenge that is already up there in simulation. And as I mentioned earlier, we're working on something that also works on a real robot, and hopefully that'll be up later this year as well.
Cool. All right. Thank you everyone
very much
for coming.
Thank you, David and Niko, for organizing this.
Thank you.
It's been a pleasure. Thanks for coming in, Walter, Larry, Felippe, Dimity, Sungwook, Songyang, and Rocio. All right.
Take